В любой карман не имеет значения. И если вы не против, я вот здесь вот.
Да, конечно. Конечно.
Надеюсь, теперь будет работать.
Okay, ladies and gentlemen, take your seats. And I'm very happy to welcome you today after a long break, more than 4 years, caused at first by some financial problems with our institute, which are over. I should tell you now, presumably we will be having a conference each year, at least for the foreseeable future. And of course, 2 terrible years of COVID when we were confined more or less to our houses, to our apartments, and forgot that the outside world existed and people could work somewhere or dine outside. So this is presumably over too. Now with this conference, we resume our series of conferences of continuous advances in QCD. With deep regret, I want to remind you that one of the organizers of this series and the participant of FTPI, a member of FTPI from the very inception of FTPI, Misha Voloshin, had died in March already 2020, 2 years ago. He came here to FTPI even 1 year before me in 1989. I won't tell much about him because I will have a few words to tell you during the conference dinner and show some pictures which we, myself and Megan, could collect, could find. Now I will tell you just that he was born in 1953. In 1953 on May 14, in 2 days from now. He was born in Bucharest, Romania. His father was a Soviet petroleum engineer who was sent to Romania to help them set up their oil and gas business. So he died at the age of what, 67, right? 66, yes. And then I will tell you a few words about his career, his life and career in Russia, and then in the United States today in the evening. So that's all I wanted to say. Again, welcome. You have all information. It had been provided to you by Alicia, by Megan, and by Alexei, chairman. Even yesterday, he made a collection of restaurants where one could have a lunch. I remind you, today we have a conference dinner very close from here. So don't forget to come and have nice dinner. And now I just announce the first talk will be from Matthias Neubert, who is right here. All-order resummation of super-leading logarithms for non-global processes at hadron colliders, solving a 16-year-old QFT problem. Yeah. Sorry for that.
It's okay. Don't flip if you want to. All the dongles.
Maybe the dongles. try to clip this and then. Okay, Misha, thank you very much for the introduction, and also all the organizers for the invitation to come back here. I have been to probably almost all of the previous conferences in this series, and I'm very happy that it is resumed now after so many years of break. Of course, I'm also was also important for me to come here because of the particular occasion that Misha already mentioned, that we also celebrate the scientific and personal life of Misha Voloshin here. I'm going to talk about, as Misha said, the resummation of superleading logarithms. Most of you probably don't know what they are. I also didn't know before we started working on this, but it is actually a very interesting and subtle problem in hadron collider physics. I also have this picture of Misha here at the outset. It's a picture that I really like because it shows many things about Misha. When you knew him, you see that, you know, of course, he was a brilliant physicist, like so many of the giant physicists at this institution, but he was also a very humble man, and he was a very positive man. He was always cheerful, and he liked subtle things in physics. So really, I think it's a great loss for our community, which is really very sad. Now, oops. Okay. Let's see. Okay. So I'm going to talk about a subtle effect in jet physics at the LHC. You all know that jets are very important at the LHC. They basically closely mirror the underlying hard scattering event. In hadron colliders, we don't see individual partons in the detectors. We see jets, but the jets tell us something about the underlying event. In this particular case, you see two jets created in the decay of a Higgs boson, two bottom quarks. And by reconstructing these jets, we can probe the standard model. We can also look for new physics. Now, jet rates, on the other hand, are also complicated to calculate because they depend on many different scales, as is obvious from this cartoon. So here I show you a two-jet event like the one you have seen before. And of course, jets are defined by the fact that inside the jet cone, you can emit as much energy as you like. This is just a collimated set of very energetic particles. But outside, in the gap between jets region, there's typically a veto on hard radiation. So there's let's say a scale Q naught here can be a cut on PT, for example, or a cut on energy, which is much less than the typical partonic center of mass energy, which I will call Q. So it's a paradigmatic example of a two-scale process. There are large logs in this problem, which can really be much bigger than one. And when one computes these cross sections in perturbation theory, one finds logarithmically enhanced terms. Now, the state of the art for jet physics is really two loop, mostly one loop, because these processes are exclusive, they're complicated. There are no three loop corrections available. So the state of the art is really two loop order, and you see a logarithmic enhancement order by order, basically. I will assume that the jets are not particularly narrow, otherwise there can be additional logarithmic enhancements here. Now, even at lepton colliders, there is a non-trivial effect happening for these jet rates. So I will have 1 or 2 slides on lepton colliders here. Because for these exclusive observables, where, as I said, high energy radiation is restricted to certain regions, namely inside the jets, and outside you only have soft emissions, the subtlety arises when soft gluons are emitted not from the primary quark, for instance, in this jet, but from secondary or tertiary partons. So inside the jet, there is some hard branchings going on, and the soft gluons can be emitted off these secondary or tertiary partons. Now, those soft gluons, they probe not only the color charges of these particles inside the jet, they probe also their direction. So they really probe the substructure of the jet, even if that substructure is not measured experimentally. And as a result, soft radiation from these secondary emissions leads to a very complicated pattern of large logs, which do not easily exponentiate. Now, actually, they're called non-global logs, and these non-global logs in some sense were defined as those logs which do not exponentiate using standard tools. Now, these non-global logs are not contained, at least in conventional parton showers. There's now a strong effort to include them in newer versions of parton showers. There are single logarithmic effects at lepton colliders, 1 log for each order in alpha. And the only known way until a few years ago to resum them was in the strict large n limit, so NC to infinity, using an integral equation derived by Banfi, Marcassini, Smai 20 years ago. So it's a very different way of thinking about logs than we usually do in terms of renormalization group language. Now at hadron colliders, non-global logs take on a much more intricate form, even more intricate than here. And no generalization of this equation exists for hadron colliders, at least it's not known. On the other hand, a very peculiar effect was observed, I should say, for these logarithms at hadron colliders. And when I say observed, it is in an indirect way. People discovered the existence of so-called superleading logarithms, which start at 4-loop order in this perturbation theories. So, and only at hadron colliders. So the first 3 orders, you would have a single log per order in alpha. Starting at 4-loop, you would have 2 logs for each order in alpha. So here it's a double logarithmic series, and these powers of logs get higher and higher. Now, formally, if you count alpha log order 1, then all of these terms are formally larger than order 1. Of course, numerically, it's a different question, but formally, this is true. This was discovered. Oh, here, always here. Q over Q naught. Q is the partonic center of mass energy, and Q naught is the TeV and 20 GeV, let's say, if you want the number. Yeah. So this observation was made in this paper, Forshaw, Kurielis, Seimer, 2006. This is why I say 16-year-old problem. And the first 2 papers they wrote on the subject had a question mark because, of course, nobody has ever calculated these logs. So they really, because it's a 4-loop calculation, they really looked at structure of diagrams in certain regions and concluded that this effect should be present, and it is present. And really, papers on this subject have only been written by this group with different graduate students, and there are about 6 papers on this problem in all the archive. And basically, it concerns the calculation of this first term, which is known for 2-to-2 processes. Now, as I will argue, really, this is a double logarithmic series starting at 3-loop order. So we will see that starting at 3-loop, a new effect arises. And the reason is that all of these superleading logs are enhanced by a pi square, which is really the imaginary part of the same log that stands here. So this log is a time-like log. It has an I pi, and you need 2 pi squares to get the effect. And then the remaining ones can be real logarithms. And if you count this pi square as log for a moment, then you see that this is alpha cubed log to the 5th, alpha 4 log to the 7, and so on. So it's really alpha to the n log to the 2n minus 1 starting at 3-loop order. And in my talk, I will basically compute this entire series, this infinite series for arbitrary jet processes, even proton-proton to 10 jets, if you wish. So this is what we have accomplished. And in that sense, it solves this old problem. Now, the physics underlying these superleading logs is a violation of color coherence due to a subtle quantum effect, namely the exchange of very soft gluons, so-called Coulomb or Glauber gluons, between the initial state partons in this hard process. So, of course, it's a proton-proton collision. You take a parton from each proton, gluons in this cartoon here. Then there's a hard scattering. Then you produce the jets. And the red gluons here are these Glauber exchanges between these incoming partons. The blue gluons are collinear emissions of these colliding partons, which is basically what you could call the underlying event. This moves along the beam direction. And the green gluons are the soft gluons emitted into the gap on which the veto is imposed. Now, one can see the source of this effect by looking at the so-called soft anomalous dimension. The soft anomalous dimension gives you the structure of infrared singularities of arbitrary m-parton amplitudes. Up to 2 loop, it has this very simple form where here one sums over pairs of partons in the process. And it's well known that there is this so-called cusp term where you get simply the dipole product of the color generators of the 2 partons, a universal quantity called the cusp anomalous dimension, and a logarithm of mu square over the invariant mass squared of that pair of partons with a minus sign here. Now, Sij is positive whenever you take 2 partons from the final state or 2 partons from the initial state. And when S is positive, the log picks up an I pi. And S is negative if you take 1 parton from the initial and 1 parton from the final state. Now, in E minus collisions, there are no partons in the initial state. S is always positive. Each log has an I pi. And summing over all pairs here and using color conservation, you can see that this I pi cancels out basically from the cross section. At hadron colliders, there is the possibility of having some S's that are negative. So this color conservation argument doesn't go through anymore. And if you work it out, what you find is that there is an imaginary part of this anomalous dimension, and it's proportional to the product of the color generators of these 2 initial state particles. And this, as we will see, this imaginary part is the source of these superleading logs. Lepton collider, these are 0, basically. The effect simply doesn't exist.
So it would be lepton collider as well?
No, because there are no colored initial state particles. It's 0 at lepton. Lepton colliders, color conservation cancels this effect, but at proton colliders, it survives. So in July of last year, we proposed a new factorization theorem for these non-global processes at hadron colliders. It is based on papers we have written 7 years ago on non-global observables at lepton colliders. So basically, I don't have the time to go through these old papers, but basically what we showed there is that the non-global logs I mentioned earlier in soft collinear effective theory can be summed using renormalization group techniques, even though this was not the traditional way of thinking about them. So we're now taking this over to hadron colliders. This is the formula we proposed. It looks like any other factorization formula. You know, I have a 2-scale problem. I have some hard functions here containing the dependence on the hard scale, some low energy matrix elements containing the dependence on the low scale. So I have factorized these 2 scales. And then once one has such a structure, normally the resummation of logs is just easy by solving RG equations, which say that the mu dependence needs to cancel here. Now, what are these hard functions? The hard functions are in the sense of a density matrix, the square of the hard scattering amplitude. So M here labels the number of partons in the process. So this is an M parton process. A and B are the partons in the initial state over which we sum. So we get the square of the amplitude. Normally you would integrate this over phase space, but here we need to integrate over phase space at fixed directions of those M partons. So N here is a set of direction vectors characterizing the M partons, and the phase space integral here is restricted to the energy integrals. And then the total energy is Q, and the total momentum is 0 in the center of mass frame. And this theta function says that basically all these hard emissions are inside the jets. So I show this just to tell you that we have well-defined expressions for these objects. These low energy matrix elements are squared amplitudes containing soft Wilson lines for each of the partons, and in addition to collinear fields for the initial state partons, all in soft collinear effective theory. Now, if it was so simple, people would have found this many years ago. This formula is non-trivial because of two effects. First of all, there is this times symbol here. The times symbol says that both the hard functions and the soft functions depend on all the directions of the particles inside the jets. And the reason is that the soft emissions, as I mentioned earlier, can probe these directions. So the trick is that you need to first multiply these functions and then integrate over these directions. That's what this symbol means. And the second non-trivial thing is that I mentioned that M is the pattern multiplicity. There's a sum over N from the lowest possible value. This is 2 plus M, where M is the number of final state jets, up to infinity. So there's an, if you wish, there's an infinite number of terms in this factorization theorem characterized by multiplicity of the partons in the hard event. And this is obvious because whenever I emit a parton, I now have a new hard parton in the jet that the soft gluons can probe. Now, this is nevertheless a useful formula because these hard functions, if you evaluate them at the hard scale, every time you emit another parton, you pay a factor of alpha strong. So if you want to work to, let's say, next to leading order in alpha strong, resum all the logs, then M here is limited to the first two terms. If you want to work to next to leading order, you're limited to the first three terms. So this infinite sum becomes a finite sum as long as you work to a given order of renormalization group improved perturbation theory. So this is the renormalization group equation for this hard function. It looks again like an ordinary renormalization group equation. There is an anomalous dimension here, which one can calculate. It's a complicated equation, nevertheless, because the anomalous dimension is a matrix in the space of parton multiplicities. In fact, it's an infinite dimensional matrix. And also its entries are operators in color space. So this whole calculation is done in color space. The color space is a tensor product of the color spaces of the individual partons. Nevertheless, if you solve this renormalization group equation, you sum all large logarithmic corrections to the cross section, including the superleading logarithms, the non-global logarithms, and all other logarithms. Now, our goal here is to resum superleading logs. And to do that, we need to solve this problem at lowest order. So what we are going to do is we're going to start with the hard functions at the hard scale, mu of order q, but only at tree level at lowest order. We then solve this equation in the leading logarithmic approximation, run down to the low scale q naught, and then evaluate these matrix elements at the low scale q naught again at tree level in the lowest order. That is the leading log approximation, and that will give us the superleading logarithms. The low energy matrix elements at tree level are very simple. You simply find that it's the product of the parton distribution functions of the two initial state partons. All the soft Wilson lines are 1 in this approximation, and corrections would start at order alpha. So this is very trivial. The soft function is basically just a unit operator in color space. And then the challenge is to solve the RG equation in leading log approximation. Of course, I can solve it formally by just writing a path-ordered exponential over this anomalous dimension. This is defined by its Taylor series, and I need to work out, basically using the one loop anomalous dimension, I need to work out the leading terms in this Taylor series. That is the challenge. And we will do this for an arbitrary 2 to m jet hard process. And when we started this, we never had an idea that this could be done analytically, but you will see that at the end of the day, we actually have a completely analytic solution for the infinite series of superleading logarithms. At leading log, we need the anomalous dimension at one loop. Here it is. It's an infinite dimensional matrix in the space of parton multiplicities, but only the diagonal and the first off diagonal are filled at one loop order. And they have a very intuitive meaning. Along the diagonal, there are virtual corrections where basically you take an amplitude and exchange a gluon here among two partons, either in the amplitude or in the complex conjugate amplitude. Remember that the hard functions are, it's a density matrix. It's amplitude times its complex conjugate. And along the off diagonal, there are real emission terms where basically you emit a gluon from parton I in the amplitude, parton J in the amplitude. You take the cut here, so it's really a final state gluon. And of course, that turns an M parton amplitude into an M+1 parton amplitude, which is why you go to the first off diagonal here. Good. So in the anomalous dimension I showed you earlier, there are terms which have this cusp logarithm, and then there are non-logarithmic terms. The terms which have the cusp logarithm upon integration give double logarithmic contributions. So in some sense, this is the most important term here. So I split up these virtual and real pieces into pieces which have the cusp logarithm and other terms. And I also factor out here in the virtual pieces the imaginary part that I showed you earlier, the so-called Coulomb phases. The coefficients of the logarithmic terms are relatively simple. In the case of the virtual corrections, it's just a Casimir, CF or CA, depending on whether we have a quark or a gluon. In the case of the real corrections, we have a color generator on a particle in the amplitude, a color generator on the same particle in the complex conjugate amplitude. And then this log comes from the case where we have a collinear singularity. So the direction of this parton is the same as the direction of the parent part. And then the Coulomb phase I showed you earlier is T1 times T2 times 2I pi, and there is a factor 4 here from the cusp anomalous dimension at one loop. Its coefficient is 4. Now the notation here is a bit funny. There are left and right indices on these color generators. The reason is that the hard function is a density matrix. A color generator with an L acts on the amplitude. It multiplies the hard function from the left. A color generator with an R acts on the complex conjugate amplitude. It multiplies the hard function from the right. And there is a relative minus sign because under complex conjugation, of course, this I becomes minus I. So this is explained again here. There's another subtlety. Whenever you have a real emission, we use this open circle symbol. Whenever we have a real emission, of course, our color space was an M parton color space. Now I emit a gluon. I have an additional parton, so my color space increases to an M+1 parton color space. There's one more color spaces in the tensor product, and that is what this open circle means. So if I apply this operator to a hard function, this goes to the left, this goes to the right, but then there are indices here on the color generators, which are the indices of the new gluon, which live in the extra color space, basically. So the color space gets more and more complicated as we emit more and more partons. And then finally, there are these quantities called V bar and R bar, which is whatever remains after I pulled out these factors. There are explicit expressions for these objects, but they don't need to concern us here, except that there is the usual dipole emitter function, which enters in these objects, and we will see later that we will get an integral of these dipole emitter functions in the final result. Now, as I mentioned, we need to work out the highest logarithmic terms in this path-ordered exponential. Now, normally you would say this is very easy. I just take always this term, because this term will give double logs, right? So I want this term as often as possible. So normally you would say that, I think the battery is very weak on this thing. Normally you would say in the nth order term in the series, let me just always take this log enhanced piece, then I get log to the 2n. Now, if you do that, you get 0. So there are 3 properties of these individual terms in the anomalous dimension, which are important. And once you understand these 3 properties, you immediately understand the structure of the result. The first property is that this cusp term commutes with the remainder function here, which just describes soft emissions when it acts on a hard function. And that is just the statement of color coherence in the absence of these Glauber phases. Color coherence says that if you do a soft gluon emission from a highly energetic particle, it doesn't matter whether the particle splits into two collinear particles, the soft gluon doesn't see the difference. It sees the total color charge and the direction. So if you do a collinear splitting, it doesn't matter whether you emitted the gluon before the splitting or after the splitting. This is what this identity says. And the other two identities say that if you have this cusp term on the very end and it acts on this one, which is the low energy matrix elements, you get 0. And if you have the Glauber phase all the way to the right and it acts on this one, you also get 0. For the Glauber phase, this is immediately obvious. If you just look at this expression here, because if it sits all the way to the right, it doesn't matter whether these matrices are applied from the left or from the right, simply because of the cyclicity of the trace. Sorry for my jumping here. If this sits on the left under the trace, you can move it to the other side. So left and right cancel each other because of this relative minus sign. And it's also easy to show that the cusp term all the way to the right also gives 0. So this is the reason why you cannot have only cusp terms here. You will simply get 0. And this is the reason why you need the Glauber phases, because if it wasn't for these Glauber phases, no matter where you have gamma bar, you could always commute the cusp term through and then apply this to get 0. So you see, we need at least one soft emission, gamma bar, and we need Glauber phases to get a non-zero result. Okay. And now you will understand the next slide, which will show you what the structure is of the leading terms in this path-ordered exponential at nth order, expanding this. The leading term must have this color structure. You need the gamma bar all the way to the right because any of the others gives 0. You need a Glauber phase next to it because if it wasn't there, then you could commute this through and get 0. And now you can have insertions of the cusp term. They will give double logarithms. But we need a second Glauber phase because we are computing a cross section and the Glauber phase is purely imaginary. Cross sections are real. So we need a second Glauber phase somewhere. So I put it here and then more cusp terms. So you see, I have as many cusp terms as I can here. I have n cusp terms, but really it's the n plus third order in the expansion of this exponential. So you understand immediately why the superleading logs start at 4 loop order, because in the first 3 loops, I get this, which is single logarithmic, and only then in 4 loop and higher, I can have these cusp terms, which give the double logarithmic corrections. So it's completely clear why this is the structure that one finds. Now, in principle, this is a monster, this color structure, because as I said, every time we emit a gluon, the color space gets bigger and bigger and bigger. Nevertheless, one finds that some remarkable simplifications happen when one starts to evaluate these traces. So in particular, working from the right inwards, it turns out that applying the soft emission, the Glauber phase, and an arbitrary number of cusp terms gives rise to a very simple structure. It's only a single trace here where you take whatever is the remaining hard function, and you have a color generator for particle 1, a color generator for particle 2, and then a color generator for any of the final state particles contracted with an FABC symbol. And the dependence on this exponent here is a very simple prefactor, 4nc raised to n minus r. And here you see these j's. The j's are integrals over differences of these dipole emitter functions. And these integrals are finite. There are no singularities. You can just calculate them, but they are sensitive to the direction of the final state jets. This is what enters here. It's this K index, basically. Now, okay, now I worked until here. Now I have to apply the second Glauber phase and then more emissions of the cusp terms. This turns out to be complicated, but remarkably, for an arbitrary number of R and N, this problem closes onto a basis of color structures, and the basis contains 10 structures. And the structures get relatively complicated because they contain symmetric products of color generators. But nevertheless, the basis is not infinitely large. The basis closes on these 10 structures. And the 10 structures can be grouped into two types of terms. There are terms here where the final state partons are involved. And in fact, J is a sum over all final state partons. And there are 4 operators entering here. And you see 1 and 2 everywhere. This is the initial state particles, but J here is the final state particle. And you see we get symmetric products of 2 color generators here. And the remaining 6 terms only involve color structures for the initial state particles. And here the most complicated structure has a product, a symmetrized product of 3 color generators. Okay. Now it's possible to derive a recursive set of equations for the coefficients of these terms by simply working out what the next insertion and the next insertion of the anomalous dimension does. And you get this system of recurrence relations which can be solved, and this is the solution. And this is the exact solution to this problem. So I've shown you these color structures and I'm giving you here their coefficients. And now if you know which process you look at, you simply plug it in here. That's the answer. You simply evaluate these 10 color traces, multiply by these coefficients, and that's the answer. We're not working in the large NC limit. You see all kinds of crazy factors here, 3nc plus 2, 3nc minus 2 raised to some power. So this is a full N result. There's no approximation in this result. It's completely explicit. This is the color structures. Now you plug them in. You have to do the scale integrals. So that gives rise to some crazy factorials. And here is the infinite set of superleading logs to a given cross section. Cross section sits inside these color structures. Kinematic information sits inside these J's. The logarithmic terms are here. Alpha is there. And you see it's to all orders in alpha. And you see it starts at 3-loop order, not at 4-loop order. But at 3-loop order, we just get 2 Glauber phases, no double logs. But it's the same physics. So from this formula, we have reproduced everything that is in the literature on superleading logs. And I told you there's not really much. But the formula contains much more because it contains the all order contributions. And it works for all processes, not just 2-to-2 scattering, which had been studied before, also 2-to-n scattering. Oops. Now, actually, the formula I have shown you has not been published yet, still unpublished. What has been published is a simpler formula, which we found by looking at initial state patterns in the fundamental representations, so quarks or anti-quarks. Because in the fundamental representation, as you know very well, antisymmetric products of color generators can be decomposed into the color generators themselves. So you never get more than a single generator for a given particle using this identity. And then these 10 color structures I showed you earlier collapse to 4 color structures, and these very complicated coefficients collapse to extremely simple coefficients. The most complicated one is 2 to the r here and there. And the 4 color structures you see here. So there's a totally symmetric DABC symbol entering now, and this is the 4 color structure. So this is the formula we published last year in our PhysRev letters, but by now we have also worked out the general case. Now let me show you one particular case where this sum over R and N can be done in a closed form. This is the case of quark-quark, not quark-antiquark, quark-quark to quark-quark scattering in the color singlet channel, so photon exchange, let's say. It's not very realistic for phenomenology, but it's nice because this double sum can be done analytically. And one finds a hypergeometric function where the argument of this function is NC alpha strong over pi times log square. Now, alpha times log square, as I mentioned, is formally bigger than order 1. And in fact, typically this W variable is of order 2 or so, but it's certainly not small. So all these superleading logs are resummed into this hypergeometric function. Here you see the pi square term, the Glauber phases. And really here you get NC alpha over pi times pi square, which is also a variable that is of order 1.3, 1.4 or so. So also this is not small. The angular integrals give the rapidity gap between the jets. So this is 2 jets in the final state. Delta y is the rapidity gap between them. And the prefactor here, now there's only a single alpha left times a log over NC. So you see that here there is a color suppression. It's very well known these superleading logs are subleading color effects. which is also why, parton showers or such things do not contain them. But you see, in essence, all of this is order 1, and the prefactor here is a 1-loop prefactor. So basically, this effect numerically can be as large as a 1-loop correction, even though it starts at 3-loop order and higher. And now the color singlet channel is not relevant for phenomenology because this is dominated by gluon exchange, not photon exchange. But this formula gives rise to these type of corrections. Here I have center of mass energy, half a TeV, rapidity gap 2. This is the scale Q0. And this is the contribution of superleading logs in units of the Born cross section as a function of Q0. And you see a band here. And you see that the corrections, let's take 25 as an example, the corrections can be anywhere between 10 and a couple of %. And of course, the width of the band results from the fact that in the double leading logarithmic approximation, the scale in the coupling is not determined because this is a single logarithmic effect. So if I vary the scale between Q and Q0, unfortunately, there is a very large scale uncertainty. This is obviously something that we are going to improve by working out the next to leading logarithmic corrections. This is the interesting channel. This is the color octet. So this is now real quark-quark scattering at the LHC. And you see that up to a sign change, the effect is of similar order, a couple to 10%, depending on the scale choice here. Now, given this closed formula, one can also look at the asymptotics. I think it will be more or less fine. One can look at the asymptotics, and one finds a very interesting and kind of shocking behavior. This infinite series of superleading logs in the limit where alpha log square really tends to infinity is given by this expression. It's a log of W. So basically, the behavior is log of Q square, which is very different from standard Sudakov behavior. Sudakov double logs, they resum into something that is more like exponential of minus constant times alpha log square. So they die out very quickly in the asymptotic limit. This thing doesn't die out at all. This thing actually logarithmically increases. Now, in our paper, this was it. Now, of course, we expected larger effects for gluon-initiated processes. And now that we have worked out the gluon case, we can also look at gluon-gluon scattering. So in these plots now, I take a TeV as platonic center of mass energy, and I compare the quark-quark scattering to gluon-gluon scattering, both in the T channel, so forward scattering. And you see that indeed the corrections in the gluon case are a bit bigger, typically between now 6 and 20%, depending on the scale choice, a bit bigger than in the quark case. If you look at the individual contribution to the series, you find actually that this thing could have been very different. So again, this is the series of the infinite tower of superleading logs. And importantly, there was this alternating sign, minus to the n here. So this is an alternating series. And thanks God it is, otherwise the corrections would be even bigger. So here for the quark case, n equals 0 is the 3-loop contribution, 4-loop, 5-loop, 6-loop, 7-loop. And you see this alternating behavior and a relatively good convergence. But you see, for instance, the 4-loop is not much smaller than the 3-loop term. But of course, it is convergent. If you look in the gluon case, it's also convergent, but the individual terms are huge now. So for instance, the 3-loop term is 60%, the 4-loop term is 60% with a minus sign, the 5-loop term is 40%, the 6-loop term is 20%. It also converges, but really it's a small effect when you sum it up because of this alternating behavior. Otherwise, the corrections would be order 1. So when I showed you this band, the fact that it's only 15 or 10% is really because of this alternating sum behavior. Individually, these terms are huge. So I think I finish on time, a couple of remarks and then some conclusions. So with this approach based on soft collinear effective theory, we have really solved this 16-year-old problem of understanding the all-order structure of superleading logs for non-global observables at hadron colliders. We understand the all-order behavior, and we understand them for arbitrary processes, 2 to n. In the formula In the final formula, you simply had to sum over all final state jets. Now, interestingly, our formula also applies to cases where in the final state there is a single or even no jet. Now, this was not recognized in the literature before. People thought that you need at least 2 colored particles in the final state. That is true. But I had many emissions of gluons into the final state when I solved this RG equation. So those can be the final state partons. So if there is a single final state jet, I just need to emit a second one through applications of the anomalous dimension. And therefore, for m equals 1, the series starts at 4-loop order, not 3-loop. For n equals 0, the series starts at 5-loop order, not 3-loop, but these effects are still there. And in particular, the m equals 1 case is interesting because, for instance, proton-proton to Higgs plus jet is an interesting observable. Also, new physics searches, let's say classical WIMP searches, proton-proton to jet plus missing energy. It will be interesting to study the effect of superleading logs for these kind of processes. Really, I mean, it's great that we are able to resum these leading double logs, but leading double log is never a good approximation. It's a very poor man's approximation. And of course, really, this is just the beginning. I think we're just scratching the surface here. So the factorization theorem I showed you, this is an exact statement up to power suppressed terms. This is really an all order factorization formula. So it will be very important to improve our understanding of this formula as much as we can. In particular, we are going to extend the formalism to massive final state partons. We want to also study top quark jets, for example. And then the most interesting part will be to understand the structure of these low energy matrix elements. For the superleading logs, I needed them at 3 level where they are trivial. Now, as soon as you go beyond 3 level, these low energy matrix elements, they also contain the so-called Glauber-gluon interactions because the whole superleading logs result from these Glauber-gluons. Now, soft collinear effective theory with Glauber-gluons has been constructed. There is a famous paper by Vainshtein and Stewart, 2016, but it has not been applied to many physically relevant processes. So this will be one of the most interesting applications of this framework. And the Glauber-gluons break factorization, really. So this simple notion that you just take a partonic cross-section and you convolute it with parton distribution functions, this assumes a type of factorization which is spoiled by Glauber-gluons. So in order to see how these factorization violations happen and you know how one can formulate more general factorization theorems, one will need to study these low energy matrix elements. Whatever we learn in this program will be relevant for improving existing parton shower codes. As I mentioned, there's a lot of work currently extending parton showers beyond the large NC limit and including non-global contributions in them. It would be interesting to see whether one can also include these superleading contributions into parton showers, because at the end of the day, experimentalists want parton showers. They want to simulate what these emissions do inside the detectors. Ultimately, this promises to give a new level of precision in predictions for LHC jet observables. So thank you very much for your attention. I hope I didn't go too much over time, but I think more or less I stayed within my 35 minutes.
Like one quick question, otherwise, any discussion. Yes. So, what's the expected value for the Higgs reducing cross-sector to make
the Higgs, yeah, so I think the question was, what is the expected correction on inclusive Higgs production? So that would be Higgs with a jet veto. I mean, if it's fully inclusive, Higgs plus anything, these effects do not arise. But if it's Higgs plus jet veto, it is one of these things which I mentioned here. It would basically, the effects would start in higher orders. But then on the other hand, as I showed you, that was bad. I showed you earlier that in Higgs physics or in general in gluon initiated processes, so basically, you know, you would look at this line, it would start here at this n equals 3 line, and then you have to resum the higher order terms. It will be smaller than 10%, but it could be a couple of percent. We are not sure yet. We honestly, before we will do phenomenology, we will eliminate the scale uncertainty. We have ideas of how to include the next two leading logarithmic terms, because this is too much of an uncertainty to do. You don't have a gain if I tell you the effect is anywhere between 1 and 10%. You want to know, is it 1%? Then I can forget about it, or is it 10%? So we'll have to do some more theory work before doing phenomenology. Okay, thank you very much. And I will remove my laptop, right? So otherwise people are free to use this one if they want. No, the microphone.
Go. And one more moment. I have to make sure that you can easily advance slides. This goes in your pocket, and this you can clip on.
This works.
This might work. So, pardon me, just to check.
Doesn't work.
No. So
Only
the laser pointer works, and somehow the slide advance doesn't. You just press these buttons, and
okay.
Yeah.
No problem. Thank you.
and there's also a stick if you want. Okay, so next we're very lucky to have Matthias Khodjamirian, who's going to tell us about new CAQCD sum rules.
Okay. First of all, I would like to thank Misha Shipman and Alexei for chairman for this invitation, and I'm happy that this long tradition of QCD advances workshops continues. And since I was always today, I will tell you something which is not published, not even finished, but I think the tradition of this workshop was always to present something which is which one want to discuss. There is a second reason I will tell about at the end why I have chosen this particular project. This is about B sub C J psi form factors. Now, what is especially interesting about this form factors? The reason is very practical, actually. It is related to, sorry, I just jumped somewhere. Okay. If you look in the particle data group tables, you will find this, okay. Oh, yes. You will find this entry. And B sub C is an interesting object of two heavy quarks. One is very heavy, the other is heavy. So you can actually think of a limit when both are very heavy as compared to QCD scale, but C quark is still much lighter than B quark. So this is the limit we are going to discuss. But as I said, there is a practical reason, because these semi-leptonic decays are now among the hot topics in the quark flavor physics. This is just actually in standard model is just B2C L nu transition. They were recently measured the ratio of these decays, tau and mu. The tau lepton and mu was measured by LHCb, and actually LHCb has a lot of these B sub C mesons because they have a huge luminosity. The meson itself was discovered at Tevatron, but now LHCb is like a factory of these mesons. And then there was a QCD calculation done in lattice QCD, numerical simulation on the lattice, where they got this number for this ratio. Now, naively, you would say this thing is independent of hadronic uncertainties because they are, but in fact, it depends on the form factors because tau and mu have different masses. Therefore, and this discrepancy has excited a lot of enthusiasm of proponents of new physics. And nowadays, people are writing papers discussing which kind of new physics can fit it. But at the end of the day, it's a problem of calculating B sub C to J psi hadronic form factors. This is just a normal form factor you can define by just taking matrix element of the weak current, and I will concentrate on the vector part. The axial part is the same. It's less it's more complicated kinematically, but it's just there are three form factors. There is only one in the vector It's a transition of pseudo-scalar meson to the vector meson. So function of momentum transfer, and lattice QCD provides these form factors in the whole region. This is a big achievement, they say, because usually they provide near the zero recoil point. And this is the plot I have taken from this latest paper, HPQCD collaboration. And don't look at these points. This is just the kitchen of lattice calculation, the extrapolations. This is their final result. And this result and other results for the other form factors, they bring this branching fraction, which then brings this number for this ratio. So that's now the question is, what should we do in non-lattice QCD, in continuum QCD? Are there methods which allow us to calculate these form factors? In fact, there is a lot of papers written in the non-relativistic QCD, which is an effective theory working with non-relativistic quarks. I'm not an expert, so I will not go into details. They just directly calculate the matrix element. There are very old 3-point QCD sum rule calculations, which I understand very well. They create double dispersion relation, and however, there is only a leading order triangle loop which contributes there, and the gluon condensate. The next to leading order correction is very difficult to calculate technically. So when we started this project, there were, of course, because our group is also involved in flavor physics, well, the question was, is there an alternative sum rule approach which can help us to calculate the form factors? Since we are mainly using the so-called QCD light cone sum rule, I forgot to say that this work is being done by Thomas Manel, whom many of you know very well, and Marcia Bordone. She was a postdoc in Siegen, and she is now at CERN. So we decided to look into this possibility. Yeah, I will go to this point. Yeah, it's very important. To remind about light cone sum rules of this type, there is a transition of ordinary B meson. Ordinary, I mean not B sub C, but B to U ds with light spectator to hadron, where hadron could be any light hadron, pion, or even D meson. And the idea is to use the correlation function where you put the B meson in the final or initial state and take the weak current. In this case, it's a vector current, and then interpolate the light meson. In this case, it's a pion with a simple axial current. Then you consider a certain kinematical region where the external momenta are far off shell. This was done in our group long ago, and now it's a very popular method. People are using it to calculate different B2H form factors. And when you consider this correlated diagrammatically, the leading order looks like that, and there is sort of higher power correction coming from this gluon, soft gluon emitted from the virtual quark line. The main point in this approach is that when you consider carefully this correlator, you are allowed to contract these U-quark fields, but you are not allowed to put them in one point. You have to expand it near the light cone. And U-quark propagates near the light cone. And this makes a lot of interesting physics, because then you eventually recognize in the non-local matrix element, which will be now, forget about U-quark, between B and heavy and light quark, B meson and vacuum. This is so-called B meson distribution amplitude, which is defined, strictly speaking, in heavy quark effective theory, and actually was introduced by Matthias Neubert and Andrei Gruzin long ago. And this is a definition. What is important for us here is that there is a function. It's not a number. You need to know the B meson decay constant. Of course, if you put x to 0, you will realize this is nothing but the B meson decay constant, but you have to know a lot about the functional dependence of this function, because it's a series of operators you have to sum up. There are different twists, and then even in the leading twist, you are not, you just need a lot of information from QCD. And then we decided, okay, let us look at this from the point of view of this method to B sub C decays. And when we did it, there was a first surprise, namely we considered this correlator, and then we decided Okay, we just take the on-shell B sub C meson. You see, I replaced light quark by C quark, and then you can make the traditional way to get the sum rule. You write a dispersion relation in this channel, CC bar. You isolate J psi, then you recognize that this is B to J psi form factor, and then you have the rest, and then you use duality, like you calculate this OP with some operator product expansion, and then you present it in dispersion form, and then there is a duality. And we know from the very first papers on QCD sum rules that the duality interval for J psi starts from 4mc square and ends up somewhere between psi to s, and so that's a normal way. I mean, it can be parameterized like 2mc plus some scale, which is not scaling with the heavy quark. So at the end of the day, we can get this sum rule in the form of Borel sum rule, or we can make power moments. So there are different possibilities here, and all technicalities of the sum rule approach started. But of course, the main point is how I calculate this OPE. Do I need something like a distribution amplitude of B meson or not? And this was our main question. When we then we decided that, of course, we have to define the oops, what happened? Oh, now it appears. Okay. We have to find a certain limit, and namely, we work in a heavy quark limit when MB is much heavier than MC, but MC is also much heavier than lambda QCD. And then we, of course, simplify our life that we replace the B sub C meson by B and C quarks, which are at rest. So we neglect all power correction just to see what comes out. And external momenta, of course, they are kept space-like, far off shell, so that we can have still a virtual C quark in this diagram, which is far off shell. But remember, it is now a C quark, not a light quark. It is propagating from X to 0, but it is heavy. And then we started to do the same things we usually do. We started to check this, is there a light cone expansion or not? We expanded in series of operators. There is some technicalities, which I will not tell. At the end, we came with this formula, which contains a certain kinematical factor. And then when you consider this factor in this limit, you would get 1 over MC, which means every power of the operators with derivative, etc., they are compensated by 1 over MC, so they are suppressed. So at the end of the day, if I believe that this limit is viable, I can neglect all this thing, and I'm left with 1 decay constant of B sub C, which is very nice because you only need 1 number, and this number is also provided either by lattice QCD or by QCD sum rule calculation with 2-point correlator, which is under control and which can be done easily. And it was done, actually. Okay, so this was not, however, the only surprise. We were lucky that, I mean, we were glad that we are really looking at something simpler than a light cone. We don't need to have headache with all this. Yeah, by the way, if I replace the C quark by light quark, then of course this suppression is gone, and you have to include the whole series, and you restore the light cone expansion, and that's yes, because it's lambda. It's not no. Okay, in this way, of course, I will not extract MC. I will leave it here. So it's it will be lambda QCD. No, there is no discrepancy in this way. And when we realize that we can calculate just the leading order in this way, so this is the leading order diagram at leading power, where M is the mass of the B and C quarks. So we neglect the binding effects of the B sub C meson. Then, of course, there are some next to leading order corrections. And then another surprise was that this is a diagram which has a pole in the p square variable. But this pole, for some strange reasons, has shifted towards large values, like you easily calculate this position of the pole, which is parametrically, I again stress that we are working in the heavy quark limit, much larger than 4mc square. Therefore, if you take q square 0, you cannot use duality for J psi. You are because your leading order is far away. If you take q square even larger and negative, it is even worse. It is shifted somewhere else. So J psi is not supported by the leading order distribution, by the leading order calculation. This is some next to leading, which I will discuss a bit later. But of course, if I go to the zero recoil point, then everything is okay. We return to the p square equal to 4mc squared. The reason is very simple. If big quark is heavy and decays in the heavy but energetic C quark, the other C quark, which is a partner, they have a large invariant mass. They cannot form a J psi. They always form some sort of jet or excited state. But if you return to the zero recoil point, the C quark, which appears at large q square, is also at rest, and so you can form J psi. This is trivial kinematically, but it comes out as a result of this simple calculation. So the leading order spectral density is beyond the duality interval of J psi. It goes back only when you calculate at large q square, but in this region, QCD sum rules are not very well because they are, I mean, we understand that it's not the best region to calculate for different reasons. How to fill the gap? To fill the gap, we can only use next to leading order spectral density if you are working in the leading power, which means that in the sum rule for B sub C, the imaginary part of OPE starts at next to leading order, at order alpha S. So B sub C to J psi form factors at large recoil are dominated by hard gluons, not by soft. There is nothing like, you know, soft overlap form factor, which is in B2 pi form factor, because you have a massive quark spectator. This is a simple thing, but for some reason I didn't, nobody paid attention to that. Another bad news is for 3-point QCD sum rules, because then if you only calculate leading order, it is not enough. You have to calculate alpha S diagram. And now, of course, this is a quite old paper with the last time it was calculated. Now you will say, okay, there is an enormous progress in multi-loop calculation. Why don't you calculate this? In fact, it is impossible with the modern. The reason is that you have many scales. If you take a 3-point diagram with 2 external momenta and 2 internal masses and 2 loops, nobody from the great experts in multi-loop calculations can provide you the. This is unfortunately the situation. So these sum rules are now deprived from being correct. But what I actually, everything new is well forgotten old in some way, because if I put MB equal to MC and Q squared to 0, I return to simple quarkonium, take charmonium, where the dominance of leading order is restored because the photon is has a small energy. And then this method practically was used by Misha Schiffman in '79. Probably he remembers to his old work by comparing eta C to 2 gamma. In this case, the correlator has real photons, and you make a dispersion relation in J psi. So that, but I remember that work very well. So it is sort of another limiting case when you have a charmonium, a quarkonium. Well, after all this interesting news, we turn to the next two leading order diagrams, where we have to calculate the imaginary part. This is the technical work. Again, the standard loop calculation turns out to be very hard. Too many scales, so we couldn't use any of the standard programs. We started to cut diagrams with CAQCD rules. And in fact, interestingly, from the point of view of physics, there are only 2 diagrams which contribute to the imaginary parts starting from 4mc square. All others have the same property. This pole goes far away. And we actually need to calculate only 2 of them. And if you look at this diagram more carefully, replace the current with the meson, you will understand that this is nothing but the perturbative asymptotic of the like Brodsky-Lepage mechanism, where you have hard gluon from one or another side. So only these 2 diagrams contribute. The left is not so easy, however. We calculated these diagrams, we calculated a lot here, but we have to be careful with infrared divergences which appear, so one should recalculate again the complete. So the numerical work is still in progress, although we have some results on the imaginary part. They look quite promising, but I cannot show you the numbers for the form factor yet. So it is practically the end of the story, summary outlook, yes. So we kind of try to develop new sum rule for this specific transition where you have two heavy quarks with two different scales. And we realize that vacuum to BC correlation function can be approximated with a local OP, which is very good. And actually the power corrections will come with soft gluon. So it will be a decay constant of B meson with core gluon current. So it's some sort of like this lambda E, lambda H parameters in the twist, higher twist B meson distribution amplitudes you Matthias knows very well. So from their paper, so FBC is the only non-perturbative parameter at leading power, but power corrections can be studied, of course, at Q square close to 0 or negative. The duality region for J psi is dominated by NLO diagrams. We still have to do some numerical estimates to go to axial form factors, make phenomenology, and finally calculate this notorious R J psi ratio. And of course, you can use this approach for other germanium channels because BC to eta C is also measurable, and it's interesting to compare. Okay, that's the end of this story, but I promised to tell you the second reason why I have chosen this project, because Misha Voloshin had made enormous contribution to the theory of heavy quarkonium. And I think what I miss today, of course, is that him sitting somewhere there, you know, and looking with his skeptical view on the slides, and then you can discuss with him and you understand much better what you have done. That's what I miss really. And I have a photo of, here, I have a photo of Misha when he was visiting Zigen with his wife, Natasha, and this is 2005. Everybody's younger and happier. Thank you.
We have lots of time for questions.
Yes.
Go ahead.
Question and a comment. So one thing, of course, I think you're well aware of it. I mean, this hierarchy, lambda much less than MC, much less
Yes.
than B, of course, in reality.
Yeah, in reality, it's not very well.
So actually both lambda over MC corrections.
Yes.
Be sizable at least.
Yes, I agree.
And also some of your estimates, the position of the spectral densities.
Yes.
Numbers are not so.
Yeah, that's true. But there is an escape. You can take negative Q square, and then everything is much better. What we plan is to calculate negative Q square and do Z expansion. Then you have a lever arm from the QCD, and that will be for practical reasons we are doing that. Not. I agree that Q square 0, of course, 4MC square is not much smaller than MB times MC. Yes, it's.
And the comment was that you mentioned that the two loop corrections are so complicated because of the many scales.
Yes.
But in Matthias Steinhauser's group,
I know.
we worked a lot in recent years on even 3 loop corrections to B to C transitions. And the way they usually do it is they start in the MB equal MC limit.
Yes.
But then they do the first, whatever, 27 terms in the
Okay.
Taylor expansion about the limit. And of course, once you have the technology to do the integrals in the general limit, in that way, you
Yeah.
still.
Okay. No, I agree that maybe one should talk to them again, because long ago when I still was in Karlsruhe, I discussed with Chitirkin, with Steinhauser, this, they said, forget about that. It's not cut. Yeah. Yes, I understand.
15 terms in the Taylor expansion, then it's okay, right?
Yeah, that's a
The
good.
same type of integrals,
Maybe.
one less scale, but the rest is computer.
Okay.
How close or how far it might flow?
Not yet, because we are working with numerics, and I don't want. It's like, you know, blinded experiment. We are doing 2 different calculations, so one to compare and then see what. Because there is some problem with numerical stability and all this stuff. So it's. But I promise to do it soon because we are on the way. at least.
You took my question. I was going to ask
Okay.
about comparison. Other questions? Of course, we'll all have time to ask more during the break.
Yes.
So
Thank you.
allow me to thank Alexander.
Thank you.
Do you need me to try to crank up the volume? Because these filters are pretty loud. Is the volume okay? Excellent. So we'll begin again at 10:50 with a talk about magic by Arkady. But in the meantime, please enjoy the coffee break. One last thing, directly behind this wall, there's a huge whiteboard which you can use for discussions, but people often don't see it because you're clustered over there. So feel free to come over here to discuss behind this wall. Yes, there's another one over there.
Поможете в смысле
Конечно.
устройства, да?
Конечно.
Это у меня есть-
Если вы хотите, вы можете свой компьютер использовать.
Да, наверное, проще, потому что я не приносил никуда, да? Потому что,
Which stick do you need? This one or any USB-C works?
ну вот, если...
Where is Alexander?
Hold on, I'll be right back.
I landed before the Turkish. So it's an interesting.
I think I saw it. Yeah, it's remote, I think, but they are in something. А где отключается? Не, смотрел как раз. Ага. Конечно. Еще? Теперь нужно попробовать play, да? Сейчас. Вот это оно, правильно? У меня же была это самая, как это называется, операция на глазах, я теперь еще спосабливаюсь в жизни.
Да.
Ну, правильно, но ближнее зрение стало проблемой. Оно используют лазер, когда делают это замену на линзу. Я стал говорить уже с Митхатом сейчас, потому что я говорил с Феликом по поводу вот этого LLR, not LLR, что интерпретация, и у него есть это, что это Е в степени. Я хотел бы...
Давайте поговорим потом.
Да.
У меня тоже есть. Я знаю, что это visualization, but it's not super useful for us directly, but I figured out what it is.
No, but this very concrete stuff there.
You can just use your own computer. Да, вы сможете. USB-C есть? Есть.
Есть.
Все есть.
Good.
Okay, it's 10:50, so we should begin. So our next speaker needs no introduction. It's Arkady, and he will tell us about magic and symmetries.
Okay, thank you. I think it's okay. Okay, so I'm talking about this recent study. I participated together with Nathan Craig, Isabel Garcia, and Zhenkang Zhang in Santa Barbara. No. Okay, I will. Try to go first to all time. You said because it's because of this I recollected the year of 1989 here in Minnesota, and it's not that good photograph, but I think it's kind of a rare moment when it got missing this way. Okay, trying to. I will return to magic, but here it is some more pictures of that period of time. I don't know. Can you recognize some people here? Okay. Larry McLaren is this upper left picture. Okay, and Steven Gazarovich and Hilde on the right, top right. And then you can see Voloshin family, in full there, and also in this picture. This left lower picture, it's I think it's the Gazarovich house, and there is some not magic there, but you see Misha is keeping his hand behind him. Why do you think he does it? You see, it's just recollecting of that because he was a heavy smoker. So it's I mean, and in this way he went out to smoke. Actually, Nelly also smoked at that time in '89. But anyway, yeah.
Unlike some of us that lose their hair, your face look doesn't change, just the color.
No, look, it's more hair there.
No, just the color. Just the color.
Yeah. But I think that maybe it's the subject I'm talking about is not some kind of interesting toy, but I think that it's kind of fits Misha's interest because remember he was always interested in this threshold production, you know, for example, and this way I of course it's a pity that I cannot discuss it with him, but it started. The name Magic Zero came from this Nima Arkady and Keisuke Harigaya, who introduced this kind of example. And what we are trying to do is to discuss it in more details, right? So, okay, so first we need some definition. What is magic zeros? So the idea is that some quantities which are suppressed without apparent understanding of symmetries or whatever. So that's why kind of the notion of hidden symmetries comes into the play, and I try to discuss this as well. Okay, and here some couple of quotation. The first one, any sufficiently advanced symmetry is indistinguishable from magic. It's not exact quotation because Arthur Clarke said about technology. So if you substitute technology by symmetry, then it would be this case. Okay, but I also giving quotation from Mikhail Bulgakov, Master and Margarita. I don't know, probably many of you know this science of black magic and its exposure. So I'm not sure that I would be the same way successful, but it's of course reminds this stuff. So I mean, for Nima, it was kind of interesting example that that he believes that kind of shows that the zeros shows this kind of naturalness of Wilsonian approach is broken, and it's so. But example is very particular. One loop calculation. It's not a difficult calculation, but to understand, you know, whether there is some hidden symmetry behind it or not, it is the issue that, and it's what we are trying to do. Okay, so no, here it is kind of reminding, you know. Yeah, I agree. You mean, but you know this everything by heart. Yeah. Yeah, it's a choice of colors. I'm sorry. I'm still. It's because of light, maybe. Yeah.
You can continue.
Yeah. Okay. No, not much. No, but it's better. Yeah. Yeah. So no, what it's reminding symmetry of say three Dirac fermions. So if you have this free Lagrangian for, yeah, so now it's much better.
Better?
Yeah.
Okay. Audience, please don't fall asleep despite the light.
Yeah. So if you start from this Dirac fermion, then you can view it as two component fermions, right? So psi is represented by E and EC. And okay, with opposite electric charges. Okay, and the symmetry U2 is evident from writing, you know, in terms of this chi, which is doublet. I mean, so you have this SU2 correspond to this doublet besides fermionic, and you have another. So you have two actually charges, right? One which is in SU2, and another one which is kind of U1 symmetry. But this U1 symmetry is associated with axial part, and this U2 contains this vector part of. Okay, I mean, no, of course, it's for mass is Fermi. So when you introduce a mass, then the symmetry is broken. But you know, still, it's interesting to analyze it in terms of this original masses series. So you see that there is mass term, and you see from expression for the mass term that no, I mean, look at this line, which is written in terms of doublets. So you can see that mass term breaks this U2 symmetry. Essentially, what remains is just fermionic charge. Okay, but say interaction with gauge field does not break SU2, because you see that here it is, I mean, clearly SU2 invariant here. It is the part which Misha Voloshin used when he discussed this magnetic moment of neutrino. And he spent quite some time discussing this. So what's important that for him that you can get magnetic moment without getting mass. I mean, and this symmetry. No, he constructed particular model where it was realized. But this symmetry was important for him in this respect. Okay, so what is a model which was suggested by this Nime and his collaborator? That it is extension of standard model, adding two fermion doublets, L and C. So it's one Dirac fermion, if you like. Okay, and then also a pair of singlets S and C. I mean, to several. So Lagrangian is written here. So it contains masses of those of this singlets and doublets, and Yukawa coupling. Okay, and H is doublet, no, standard doublet of Higgs field. Okay, so no, as I already mentioned, because of the masses, only U1V symmetry survive if you have this situation, and even say PC and T generically broken. No, because you have some number of constants, some which could be complex, so it's possible to break even T. No, and the simple consideration refers to the following: that let's consider that masses of these additional fermions are high, much higher than say this electroweak scale V. And so we can treat this standard model leptons, for example, as massless. Okay, moreover, gauge field also not included. So it's just kind of model where you have Higgs interaction, but not, I mean, so only in this sense, only longitudinal part of the W present. But as I said, it's more academic point. So you can include, say, some parameters and see what's going on. If say include mass of W, I will maybe mention this later. But the issue is here. So you have this one loop correction, which is simple to calculate due to this singlets and doublet. Okay, there is a certain combination of we have four this Yukawa coupling. So here it's you can notice that this YV prime part enters, but there is also YV. It's another set of diagram, but it's we can choose this particular combination to present, but we can you can do it for the other part as well. So the first diagram it is for the mass, and you see that it's a normal kind of logarithmic loop here. And as for the dipole, you know, the dipole should be convergent, right? In this case, and the point is that this diagram vanishes, this lower one. Okay, where you have this mixing of singlet and doublet due to external, Higgs field. Okay, so here it's an example of this showing how it, no, there are different ways how to show it, but one particular one, it's just written this diagram, which I showed before. And you can see here that, I mean, P is P and Q are external momenta. Q is momenta of photon and P is momenta of lepton, external lepton. So what we consider is magnetic moments of, say, electron in standard model, how these heavy fermions contribute to this moment. So what is written here, I mean, in the second line is that expansion in the external P and Q. So considering P and Q small, and remember this doublet. I mean this. I mean magnetic moment. These moments are first order in Q. So first order in Q is sufficient. So you can see that, but you can see that after expansion you can see immediately that it cancels out. Yeah, the term linear in K mu vanishes upon integration, and then you have this K mu K nu substituted by K squared eta mu, and you get it 0. Okay, so the way Arkady, Hamet, and Harry replied interpret this technically as 0, they said that integrand of this stuff is a total derivative. And then you have integral of total derivative, and okay, and in this way, you know, you are getting 0 because of infrared length of this derivative contains 0. Okay. Here it's a little bit different calculation. They are different from there only that by shift of moment. Okay, integration variable instead of K could be shifted by P and Q. But say, for example, if you go beyond this, say to the second loop or introduce mass of W, whatever, it would be no 0. So it's not like this kind of general symmetry immediately tells you the result. Okay, so no, here it is. Efforts to try to analyze this stuff, and it's related to, yeah. No, not state zero. It becomes non-zero at 2 loops and becomes non-zero if. Where? I see. Okay. You see, it's a proof of my age. No, I was intended to say the opposite. Yeah, I should say no. The 0 does not stay in the second loop, so not is omitted. Sorry. No. Yeah, no. The point is that whether the idea is that if you have kind of in this certain limit, I mean 1 loop, whatever, you see this phenomenon, the appearance of 0. And the idea is how we can understand it, whether we can explain it in kind of terms of hidden symmetry, or we cannot. The symmetry, whatever it is, it would be broken by second loop, and I'm sorry about my typo. So, okay. But yeah, so in this way it's not universal. But the reason why say Nima was particularly interested in it, because it's the question which could be related, for example, with what could be notion of hierarchy, right? Or like why certain quantity are small, So yeah.
It's not 0 at 2 loops.
Not 0.
Probably if it was not Nima, nobody
Sorry? What? Say it again?
No, there is a much more interesting violation of natural that Alexei found collaborators.
Yeah.
Actually, zero to all orders.
Yeah, no, no.
It's not in the standard.
No. Okay. He's. I'm trying to say that his magic is not black, and this magic is black.
Can I ask you, the non-zero MW also kills it?
Mass of W also killed it.
Already at one-
Also in one loop, if MW non-zero, it's also non-zero.
But
No.
MW is not.
Of course. No. Right. No. Then you can discuss what is the smallness or whatever, right? But certainly.
So it's still somehow so it's suppressed by MW.
Yeah.
It's suppressed by
Yeah.
MW.
Yeah. Right. Because. No, look, here we are talking about expansion in 1 over heavy mass of fermion, right? Okay, and so in this way, when it's non-zero, you still can discuss, yeah.
There is a famous non-renormalization theorem for symmetric H that the prophetic moment is not consistent.
Yeah, I know, yeah.
So maybe at one look it looks like.
Yeah, no, but it is the idea of our search, right? That can we find something which would, in supersymmetry, for example, it's the exact statement that, but there you know how it goes, right? That it's actually, by the way, it reminds the statement that, for example, say if you consider gravity, interaction with spin is not normalized. Analog of moment is not normalized, and there it's very simple, right? Because you can say that interaction with Christoffels, and not only the mu part is universal, but also Christoffel part is also universal. Supersymmetry, in certain way, acts a little bit in the same direction, right? That you cannot write a supersymmetry in supersymmetry terms which I mean correspond to breaking. Yeah, right, but what we are talking about is just the level of simple operator, which operator could appear or which not, right? So this is this way. Okay, so I'm sorry about this omission. Now I'm going back to analyzing this integrand. So here it is kind of simplifying the example, considering just one charge Dirac fermion interacting with massive scalar field phi. No, it's more which also charged. So interaction is that you have this new fermions, singlet and doublet, they are neutral and they're inside of the diagram. And externally, you have, say, electron, you could have muon, and then this expression could be written in the form which is written here, where h of k squared is the amplitude of scattering of this charge field phi, which is in our case it's like a charge Higgs in the example before, and we introduce this small mass of for this hill phi to have kind of infrared regularized expression, because if you will expand this in external moment again as we did before, you will find out that the answer in first order in external momenta is proportional to lambda square. Here, and look at this expression, it's clear that it's dominated by k square of the order of lambda square, right? So you see the answer that for that the answer is expressed through the amplitude at zero energy. So this scattering amplitude taken at zero, it gives you the answer for this magnetic moment. I hope you can recognize this, that it is it's written here in this form, but on the equation of motion, it is the same as a magnetic moment. So it's a standard normal one. Okay, so Okay. So this expression, notice this is real part is magnetic moment, and imaginary part it is electric dipole. I mean, but I didn't specify H yet. So if you consider this Yukawa type of interaction here, then we can calculate H explicitly, and here it is the expression for the H, and H of 0 is expressed through product of this Yukawa coupling. Okay, now when we consider this original models we started from, then you have something like sum of this double product divided by m, sum over different fermions which are there inside of this kind of scattering. Okay, so I can return back to this diagram which was there. You can view this diagram as kind of product of scattering integrated with the propagator of scalar field. So this vanishing of H of 0, for example, was very nicely explained by Arkady and Harigaya, because they said that if you try to write down, and it should remind this example of supersymmetry, because if you try to write effective operator for this small energy scattering, then operator we will need for this diagram would be this LH dagger HH multiplied by lepton. Okay, but because of this kind of H is doublet, this operator is automatically 0. So you cannot write this operator in this order, and in this way, it's kind of indeed explanation of 0 based on vanishing of this scattering amplitude at small at this order. But we tried to find alternative, trying to see whether we can find a kind of some symmetry which explain why this sum over y two hypercharges divided by m, why sum is 0, alternative to this one. Okay, so it's a different direction. Sorry?
This infrared dominance. I mean, when you put in a mass parameter lambda, you get the region a squared over lambda. But lambda is 0, right? So
Right, but the answer is non-zero if lambda equals 0. You start from it's like infrared regulator. You because remember it was 1 over k squared minus lambda square cube. When you integrate out, you will get 1 over lambda square, and then okay, yeah, but look, remember QED, right? You also introducing, say, bottom mass as a regulator, not as you're not implying that bottom mass is non-zero. No, it's finite, but it's finite even from non-zero lambda, right? The question is that that you can up to. Sorry.
this is just in the method of regions. This is just one of several regions. It's not the entire.
No, it isn't. In this particular case, it's entire integral. Why not? It is. I just took an expression for the diagram. It's nothing else. You can rewrite it. Yeah. No. It's one of the way calculated. You can, for example, the way this Arkady tried to do it, they didn't introduce lambda, but they said that it's an integral total derivative, and the integrand is 0 at this infrared end. What we are getting this way is the same, right? It's not different. So in both cases, I would say it in infrared dominance, whatever way you use to get it. So if you do not like introduction of lambda, you still need to understand what's going on this lower end, and you will come to the same result. So it's associated with which even different depending which how I rename parameters of integration, right? However, there is no problem in the sense that whatever I do, the final result would be still 0. So in this way, there is no kind of ambiguity in this result. Okay, so here it is. No, but you see, because we are playing particular game with particular masses, and in this way, when you're going to two loop, the integral, I mean, doesn't you cannot express this, for example, as amplitude at zero. I mean, in a simple way, right? So because there are not one Higgs field there, but I mean more. Right? So no, I mean, maybe you can identify it, but okay, but I mean that it's certainly non-zero. And we also check that if you will take mass lambda square non-zero indeed, the answer is non-zero too. I mean, keep lambda square. I mean, not limit lambda square goes to zero, but keep it non-zero. It's enough to see that the answer doesn't vanish. Okay, so here it is an example of this simple model. That you have this not one fermion as before, but two fermions. So it imitates this original model, and then you have this diagram. You see this; they are different. Which side, you know, first fermion or second fermion is there. So it would give you some of this contribution as compared with what was doing before. So here. We can even check that, I mean, how it relates to original model. And here it is relation, how masses are related. One mass is mass of doublet, another mass is mass of singlet. Okay, this Yukawa coupling is also written. And then you can check that this contribution of two fermions are opposite side. I mean, so and it is kind of this stuff. However, you see that, how to say, what appears here, it is this, in this consideration that it is, you can, how to say, that what we're using here, no, here, Matthias is written, it's to go to diagonalize the basis, to use a particle with a certain mass. So that's why it appears here. But this, that's the fact that this cancel out is based on this kind of spurious symmetry, because the symmetry when you are changing everything without a head to everything with head. I mean, and then you can see that that it's enough to get this relation. But it's not a symmetry of the theory, right? Because you are changing stuff between, say, different masses. Relation between, say, let's say that singlet is much lighter than doublet. Okay, and it is this, it looks like this conspiracy, right? Is that you have UV-IR conspiracy if you say that lower one is like infrared and upper one fermion as then, and it is what say Nima was trying to discuss that this conspiracy, and it was yeah, okay. 10 minutes, I see. Okay, because I decided that it maybe it's just 0. Okay, no, I do not have much. But no, in particular, they discuss this kind of intermediate range. Let's say that you have ML much larger than MS. Then you can say, aha, I'm trying to write down effective field theory in between two there. And because cancellation was between, you know, this infrared and then it sounds like kind of for series who are living in between, sounds like a kind of very special case. How infrared could be cancelled by ultraviolet? Okay. So, however, we try to follow this as well. That it's interesting that it's scheme dependent statement, because even when we introduce the effective theory in between and start to calculate contribution to dipole moment, then of course you can use, say, dimensional regularization and get some answer, and it looks like you have kind of cancellation of two different stuff. However, if I will try to use this Pauli-Vilas regularization for this calculation. Then, interesting enough, this Pauli regulator plays the role of cancellation themselves. So then you're getting cancellation, you know, kind of this UV stuff and infrared stuff, and then it doesn't look like cancellation between them. Of course, it depends. I choose this particular regularization, but the answer is still zero. I mean, the difference is that it's zero in each stuff. Okay, so here it's my conclusion that this Spurian analysis could help to understand this this cancellation in one loop, and in certain sense, you can say that sanctity of Wilsonian notion of the rise can be preserved. However, this UV IR conspiracy still looks interesting. That once you have this situation, that so maybe it deserves more studies, in spite of the fact that it's not the scheme dependent. Okay, so. In principle, it could be interesting for further study or relation between operators, which appears in effective field theory. It's not clear how much it would help to this hierarchy problem, but it's a little bit unusual way that when you have kind of loop, no, I don't know if I would be thinking about something comparable, like say Goldstone particle, right? Because in some way this H Higgs, but here it is not about kind of expanding in momentum. This Goldstone particle, they're inside, right? That in the loop, and that the fact that integrand is vanishing allows you for vanishing of the loop. No, I mean this kind of infrared dominance which is there. So I would say that my kind of disclosure of black magic maybe is not successful, but still remember in Bulgakov's book it was no disclosure at the end. So magic maybe is still there. Okay, thank you.
Depends on the model. You said that basically this is a one model phenomena, right?
No, that's true.
When Valushyn was doing something, he had this magic zero.
No, right. No, he also has a couple of models. Remember, it was not a kind of arbitrary statement, right?
Yeah, but it was not a zero.
No, but it was a relation, right? Here, in this sense, a relation, in certain sense, is simpler, right? Because it's a relation about vanishing. And I said that kind of this explanation by original authors that there is no operator associated with kind of external Higgs and magnetic moment at low energy. It's sufficient to understand that there's zero, right? In this particular case. And in certain sense, it's a symmetry of original standard model. It's not kind of new symmetry, right? The statement that the Higgs is doublet, it is a part of this original symmetry.
Why two loops?
No, because then it's not one Higgs. Because no, here when I said it, I already kind of instead of loop consider scattering amplitude of Higgs scattering on lepton, right? When you consider say two loop, it would be more complicated amplitude involved, right? So in this way, the relation would be not that simple.
Just expressing my being puzzled about the name of magic zero. I mean, there's a very standard technology called integration by parts. It's used in all loop calculation, and it always starts from a zero. You take the loop integral, write the total derivative.
No.
And then you get a relation between the
No,
function of loop integrals. They get the
No, that's true.
I
Right.
can give you a relation involving 108 three loop integrals, and they add up to zero.
No. But I think it's not the same. No, I understand what you're saying. Of course, you can integration by zero and shift variables is the same story, right? No. But in relation, you are talking about. You are not saying that magnetic moment is zero. Here is a statement about.
You have a particular integral in one loop in one model.
Yeah.
That evaluates to a total derivative.
Right, but the point is how you can.
It's not a magic zero. It's also not a hidden symmetry. It's an accident.
Okay.
Zero is a valid number.
No. In some way, it's not an accident because you can prove why it should be zero. So you can say that you can prove that it is total derivative, right? No, it's the same.
At one loop.
Yeah, it one loop.
Can I ask a possibly related question? So
Yeah.
do I understand that correctly? That the idea here is the order of results is somebody did the calculation, found the zero, and then you have some way of seeing that it should have been zero.
Yeah.
So is the statement that there are some cases, maybe this one, where you can give an a priori argument without giving it
Yeah.
that it had to be zero?
Yeah. Right. Yeah. This symmetry I'm talking about, it's enough. Yeah, I didn't emphasize this, but that you can you can prove that it is zero without explicit calculation using this symmetry.
So can I ask a
But that
related
depends
question?
on being able to write it as a scattering amplitude.
Yeah. Right. Yeah. No. That's true. But when I can write it, but then when I'm analyzing in terms of this product of Yukawa coupling divided by m, then I can use just symmetry to show the sum over this term is zero. So I do not need calculation. I need just to say that the symmetry automatically makes this stuff equal zero. I mean the sum over this Fermion, and it's alternative to total derivative. You see, it's kind of a different way, right? So we try to use to find out something which looks like some symmetry, but it is, as I said, it's Spurious symmetry because it involves these different masses. Yeah.
I didn't understand. Is the symmetry exact or is it approximate?
No, to the extent we are doing this one loop calculation, this Spurious symmetry is exact.
I mean, to one loop.
To one loop, yeah.
But then it's not exact.
No, it's not. No, but Spurious symmetry, how it, I mean, you're writing, okay, let me be more careful. You're writing this model. In the model, you introduce this neutral fermions exchange, and you have this model in such a way that changing from one fermion to another, it's exact symmetry. Okay, in this, but it's not enough, right? Because they are different masses. So some this interchange. So originally, if you start with massless fermions, the symmetry was something like Q6. I mean, because some number of massless particles, whatever. Then you introduce this, and then what we find out it is like product of U1 symmetry multiplied by symmetry of interchange. But I am trying to repeat that it is Spurious symmetry, right? It's because it's not. No, I mean interchange for parameters of particles with different masses. Yeah, so in this sense, it's kind of sufficient for one loop, but it's not sufficient for two loops.
Let's thank Arkady again. And then we can grab it.
You can use it if you want. Oh.
So what I'm going to do is run this. Sorry, I'm going to do one time here.
now it should work. You know best how to go to full screen. Do you have the microphone? Here. This goes in your pocket, and this has a clip you can attach. Or you could use the laser pointer, whatever you prefer. Okay, so our next speaker is Sasha Monin, who will tell us about multi-particle processes and semiclassics.
Yes, just a second. I have to figure out how to.
Up and down.
All right, yeah. Morning, I think it's still, yeah. Good morning, everyone. I'm happy to be here. It's, yeah, it's a bittersweet feeling today. It's always good to be back to the place where you graduated from, but unfortunately, we're missing Misha Voloshin here a lot. I'm not going to be talking about any memories. I think Misha Schiffman will talk more about that. It just brings a lot of emotions, and yeah, I liked working with Misha and actually with both Mishas. So today I'm going to be talking about multi-particle processes and large charge in semiclassics. And this work is done in collaboration with many people, and it's a mishmash of several papers. I'm not citing them here. One of my collaborators is Gabriel. He's here today. He will also be presenting some of his new stuff, I think, tomorrow. So let's start. I'm going to start with a slightly provocative statement that fundamental physics is not about. It's first of all, it's about writing equations and not solving them. But I would argue that solving equations is also important. Yeah, and our main tool for quote unquote solving equations is, analytically at least, is perturbation theory. So, however, perturbation theory doesn't work always, and there are two classes of cases when it doesn't work. First is when the coupling is large, period. We probably cannot do anything. And the second case is when the coupling is small, but there are other parameters that render effectively the expansion parameter to be small. So famous examples are scattering with many particles in the final state. When there is another parameter that I call n here becomes large, and usually when n is parametrically larger than some inverse power of lambda, perturbative expansion breaks down. So in this talk, what I want to tell you, I want to tell a story when the certain regime of weakly coupled theories, when lambda is small, however, another parameter is sufficiently large, with lambda n being fixed, can be still treated analytically. So now I'll start with a very, very simple example that encapsulates everything that I'm doing here. So imagine that I want to find the following function, which is defined as an integral. It's like a moment of some x to the power 2n with this integral, and lambda is considered small here. Of course, I can compute this integral perturbatively, just expanding this exponent in lambda, and this is what I get. Every single term can be computed analytically, and this is my result. Obviously, that when n is sufficiently small, say 1, 2, 3, it's a good expansion. However, when lambda becomes large, since gamma function grows exponentially with n, it means that the second term starts dominating the first one. So in this regime, when lambda n squared is bigger than 1, I cannot trust this computation anymore. Okay, what can be done? We can slightly improve our computation. Is we can show that actually just factoring out this parameter, this gamma to the of n plus 1/2, we can show that everything else can be exponentiated into this nice form, and it somewhat improves this computation, making it not lambda n squared, but lambda n. Okay, but still for lambda n sufficiently large, we cannot trust this computation. However, the form of this exponential tells us that if we look closer, like a guess, that the result actually is given as a semiclassical result. It's minus n in here, and here we have some expansion in terms of lambda. Yes. Oh. No, I'm just, it's just expansion in here. If I expand now gamma of n into using what? Stirling's formula, right?
You're right. Let's say
No. Yes, but it will be here as well, right? You see that here it's effectively lambda n squared, right? So it starts from, I factored out this gamma n, and effectively in here, right? If I expand now exponent, it's indeed lambda n squared. I'm just saying that corrections, not the absolute correction, but the relative correction, it goes to, there is an overall factor n that is here. In here, yes, of course. In here, it's plus order, yeah, something. Yes. Look, this one you can forget. What I'm trying to say that this ratio is given by this form, and this form suggests that it's somewhat like a semiclassical form. There is an overall minus n, and there is an expansion in 1 over n. Okay. So, and the way to do it is pretty simple. Right, I consider this integral that I started from. However, now I'm not going to be computing this integral around the saddle x equals 0. I need to compute it around a different saddle. What is this saddle? I just exponentiate x to the power 2n. I put it in as a log, and I find the saddle point for this function. And then everything can be computed. Okay. Then I can reproduce all this functions. I'm not presenting it here, but the logic is this. Okay, so this is what I want to do. I want to focus now on just O2 symmetric model, which is just a simple scalar field, massless. Okay, and I want to be in the Wilson-Fisher fixed point, so in 4 minus epsilon dimensions, and in this conformal field theory, there are 2 classes of observables that I can compute. So one class is Euclidean observables. The standard, what is called CFT data, is dimensions of operators in this theory, fusion coefficients, and also in Minkowski signature, there is a different class of observables. Those are light ray operators that are related to QCD, and I hope I'll get there. So let's start. It's going to be just a crash overview of what we call Wilson-Fisher fixed point. So we go to 4 minus epsilon dimensions, right? And the scaling dimension, say, of an operator phi to the n is given. It can be extracted from just a 2-point function. Okay, and this is one observable that we have. Fusion coefficient for any operator O can be extracted from this 3-point function. 3-point function is fixed in CFT up to, yes. No, it is. It's the other way around. If it's equal to 4, then only free theory is conformal. But if I go to 4 minus epsilon, it becomes conformal even for lambda not equal to 0, but lambda should be related to epsilon. So yeah, I'm showing it here. Yes.
In 4 dimensions, this is definitely a scalar invariant theory. It's whatever theory, but it's a scalar invariant theory.
No, this is scalar. No, this is not scalar invariant in 4 dimensions. Lambda runs. Yes, lambda runs.
Ah, because of the quantum anomaly.
Yeah, of course.
Okay.
No, this is a.
You are talking about classical.
No. Yeah. I'm talking about Wilson Fisher. Here's the explanation. So I'm taking this theory in Euclidean signature. Right now, the standard renormalization for lambda 0 implies that it can be written in this form. I can now compute the beta function. And the beta function, what we usually call beta function, is just this, beta 4. Right? However, in d not equal to 4, there is another coefficient. It's like a classical coefficient, right? Corresponding to the dimension of lambda. Lambda is not dimensionless in d not equal to 4. And one term cancels the other. That tells us that fixed point lambda star is related to epsilon. Okay, so now if we compute it to second order, we see that for small epsilon, that's a consistent expansion. It's every next term is smaller than the previous. All right, so the dimension, as I said, can be found from just a 2-point function, and classically, obviously, it boils down just to classical scaling dimension, or mass dimension of a field phi, right? So which is given by this. However, alternatively, we can also compute it just renormalizing our operator, right? Obviously, it's just multiplicative renormalization, and compute it in this endpoint function. With the insertion of renormalized operator, then anomalous dimension is given by that. And so here's basically the computation in terms of diagrams. Here, this is the insertion of phi to the n, right? And if you take into account just one loop, there are n times n minus 1 ways of attaching the vertex phi bar phi squared, right? So this one is proportional to lambda times n squared minus n times a pole. At 2 loops, this one is proportional to lambda n squared squared. There are terms that are like this. So the important thing is this, that anomalous dimension is given by this expression if you compute it. Okay? There is anomalous dimension at one loop as well. It's given by this. This is the one loop anomalous dimension. This is 2 loop anomalous dimension. So obviously, as before, as soon as n becomes sufficiently large, there is no way I can trust this result. So what am I supposed to do? Again, reshuffling, you can see that taking into account just lambda n, here lambda square n square, the leading in n term, I can write it like this. Again, it suggests that there is a certain semiclassical expansion. So there is lambda star n over lambda star times a function of lambda n. The same goes here. Here I do not have any 1 over lambda star, but still it's a function of lambda n. So yes. Look, yes, there is a counting argument, but I cannot go up to any order. I think I can argue up to probably, Gabriel can correct me if, up to 4. I think we can count to up to 4, but not more. I'm going to present what's the correct way of looking at this result, and then it becomes obvious that it's a function of lambda n, and the structure is precisely this. So no, at n equal 1. No, at n equal 1, this one vanishes. No, it doesn't. Yes. Yeah, it doesn't vanish. Exactly. Yeah. No, I heard it. Precisely. Nothing is magic here. So yes, it's very similar to what we do in RG resummation, right? There are 2 parameters. One is log, the other is lambda, and we're working for lambda log fixed. I'm sorry. Yes, and we're working in lambda log fixed, and we can do the resummation, right? This is what I'm doing here. So let me tell you how to do this computation semi-classically. Semi-classically, what I'm interested in, I want to compute this 2-point function, say, okay? And then instead of computing saddle for just the action, I exponentiate both this phi in there, and I'm looking for a saddle that corresponds to the full quote-unquote effective action in here, right? So I have to minimize this expression. Now, just rescaling fields, I see that it's the form schematically is just 1 over lambda times a function of lambda n. Mm-hmm. Mm-hmm. Okay. Look, probably I'm not that much familiar with that, but yeah. Okay. Okay. So look, now just going back to your question, look, in here, obviously that when I compute the saddle for this expression, it's lambda independent, right? It will depend only on lambda n. Lambda is just an overall parameter. So lambda is a loop counting parameter. Okay. So at first order is going to be some function of lambda n plus lambda times function of lambda n and so on and so forth. So that's the argument of how I can get to the previous statement. So now to the computation, just varying this action, right? I get this equation that's a standard equation plus some sources that originate from these two terms. At small lambda n, those are solutions. And yeah, so basically, and for arbitrary lambda n, it's thanks to Gabriel and Joao Penedones, there are solutions that are written like this with the coefficient mu derivable from this expression. So now plugging back to the 2-point function, this is what we get. Okay, there are several comments in here. So first, from here we can read off the anomalous dimension immediately. And it's exactly the same as what we obtained from just the perturbative computation. Okay, you may ask, why would we care if we can do the diagrammatic computation? We care because this one can be extended to arbitrary lambda n. Because here I'm not restricted to only small lambda n. I did it for small lambda n by using those solutions just to illustrate that I'm getting the same result for n large. And second comment is it's important that in this regime, I'm considering lambda small and n large. Okay? This n large, only for large n, this expression becomes n factorial. Okay? However, for the anomalous dimension, I can reconstruct the full result at any loop of a diagrammatic computation because it's polynomial in n and it truncates. At certain order, it truncates and I do not get any other corrections in n. All right. So the next step is, in general, it's hard to find a solution for this equation of motion that I wrote. If I'm not in 4 dimensions, it's hard to find this solution. So the way out is to use a property of conformal theories to map from a plane to a cylinder. And this operator state correspondence then tells you that whatever operator you have on the plane, it corresponds to a state on a cylinder. And the dimension of an operator on the plane is just the energy of a state on the cylinder. But then we know how to compute correlators involving states with the lowest energy in a certain sector. How to do that? You just say, imagine that I take this evolution operator and I consider the matrix element with respect to any state psi m, then at large Euclidean time, the leading contribution will correspond to the lowest energy state of my theory. And the only assumption that I'm making here is that the lowest energy state, or the operator with the smallest scaling dimension of charge n, is given by phi to the n. Okay. So what does it mean to map this theory on a cylinder? I'm just taking this theory and putting it on the cylinder. This is the term. It's like a mass term, which is actually generated by coupling to curvature. So the way to make it into a conformal, it should be phi square r, right? And on the cylinder, this r is just a constant. Okay. And now for the choice of psi n, I'm taking almost like a Fourier transform of a state with a fixed field. I'm transforming any field can be characterized by phi, by a radial mode and the argument, right? And I'm Fourier transforming with respect to alpha. Obviously, this state has charge n. Now I'm just plugging it in here. I just have to minimize this action. That comes from choosing a specific state. Those are equations of motion. That corresponds to fixing the charge. And now the solution can be written in terms of rho is constant and only the phase that changes linearly with time. Don't bother about this imaginary I, is because it's Euclidean time, but not the real time. Okay, so what it corresponds to, it corresponds like a superfluid phase of our model. So phi becomes like f times the oscillating exponent. Okay. So now plugging it back, what we can do, we can find that mu from here, it can be solved. It's just a cubic equation for lambda n. It is this form. It has this form, and yeah, it's regular for t equals 0. So I can consider the limit lambda n going to 0. It's regular, similarly to resumming logs in RG. Now plugging it back to the effective action, we get this expression for the exponent, which is basically just the anomalous dimension. And for sufficiently small lambda n, we reconstruct the diagrammatic computation, but we can go further. It's a function for arbitrary lambda n. Now we can take lambda n, whatever, very large, and then anomalous dimension scales as lambda n to the power 4/3. Okay. So what about perturbations? I can also consider perturbations here. Just take the profile rho equal phi, perturb it by r, by some coefficient pi, and then consider the quadratic Lagrangian. This quadratic Lagrangian is not diagonal, it has kinetic mixing. And then you have this spectrum of phonons that live in this superfluid phase. And this spectrum is given omega plus and omega minus. The interesting property of this spectrum is that omega minus of 1 corresponds to, it has exactly omega equal to 0. Omega equal to 1, I'm sorry. Now you can find, obviously, correction. That will be a correction to the lowest energy state. And at the same time, you predict that there is a spectrum of operators. There is a spectrum of energies. Therefore, there is a spectrum of operators. This is the lowest one plus arbitrary phonon excitations. So there is this Fock space structure. We have creation operators that correspond to omega plus and omega minus. And as I said, omega minus of 1 is exactly 1, and that corresponds to a descendant in CFT. However, the question is what these operators are. Now we know their spectrum, but what these operators are in terms of phis. Okay, so the way to understand what these operators are, Ka can be is how many of those phonons I create. Okay, so I have phonon with energy lambda I, and I can create k of them. Ki. Yes. Yeah, if you view it as on the cylinder, that corresponds to energies of a state, right? I just said that this is the energy of the lowest state on the cylinder in a sector with fixed charge n, and those are fluctuations. Those are excitations, okay? And yeah, I'm just predicting the spectrum of a theory in energy, spectrum in energy of a theory on a cylinder. But then I can just move back to the plane and to say that those numbers are just dimensions of operators on the plane. Yeah, this is where this primaries. No, all of those are primaries if I do not take into account lambda I, lambda 1, omega of minus of 1. If I do not take into account omega minus of 1, all of those are primaries. Mu, yeah, this is the parameter mu in here that physically, yeah, physically is lambda m. It's a parameter of lambda m, but the dimension comes from the radius of a cylinder. Yes, exactly. Here I put it to 1, but look, no. In CFT, cylinder is exactly, it's conformal. It's not, even though you introduce a parameter of a sphere, it's not breaking of conformal symmetry. Is it guaranteed? I'm assuming that that corresponds to a scalar. Therefore, I think it should be. It's self-consistent. If I assume that it's homogeneous, it's a solution, and this is what I have. Yes. Yes. Yes, it is an assumption, which, yeah, and I can find this solution, and then everything else follows. All right, so what about identifying operators? I showed you how to build dimensions of those operators, but now I want to understand what those operators are. For dimensions of operators are smooth functions of lambda n. Therefore, I can, at small lambda n, I can do perturbative computations, and there I can match my computation that I presented and perturbative computation. Actually, I can even do that for lambda n exactly 0 because my computation, semi-classical computation, does not rely on lambda being non-zero. I can do that just for large n. So now let me, instead of talking about 4-dimensional theory, let me study 3-dimensional theory, but this is just for simplicity, so that I do not have to think about spherical harmonics on 3-dimensional spheres. And I'm going to be thinking only about spherical harmonics on 2-dimensional sphere. And I'm going to be focusing only on very specific class of operators that I'll discuss. So I take this theory, which is just free theory, and I want to understand what are the primary operators in this theory. And I'm discussing only operators that have deltas, but they do not have epsilons. So I do not consider operators that are axial. I consider only polar operators. And moreover, I do not want, this is just a schematic thing, meaning that it's d mu1, d mu2, d mu3. And also there are some boxes. And now let me forget about those boxes. So there is no d squared. I'm going to be studying only operators of this form. So it's like derivatives scattered, sprinkled among n fields phi. Yes. Say it again. Delta is a Kronecker delta. I'm just, it's a schematic thing. I'm just saying that all terms, all indices are contracted using delta, not epsilon. Okay, there are no parity breaking operators. Yes, in free field theory, I want to classify primary operators. This is, believe it or not, this is not a trivial thing to do. No, I'm just implying that now later I can associate. Now imagine that you do computation on the way I present it on a cylinder and perturbatively, like just diagrammatically, right? Then you can match one onto the other. You know what corresponds to what, and then for large lambda n, you just analytically continue for large lambda n, and this is what you call operator with this dimension. Okay, so I'm interested in operators like this. Now, if I introduce, just for simplicity, those coordinates, I just need to understand what happens with d minus derivatives. All the rest are related, obviously, with just SO3 transformations. In free theory. Yes. Yes. Yeah, but this is not what I'm doing. I'm not adding later those operators to the Lagrange. No, I'm not doing that. So now, just first, I want to count how many. Yeah, I'm doing very badly on time, but I'll try to speed up. Look, I just want to compute. First, I want to understand the number of primary operators. Okay, I'm starting from the number of total number of spin L operators, right? It corresponds to the partitions of L into at most n integers, right? So it corresponds to how many I have to distribute L derivatives among n fields, right? So any partition can be associated to this Young tableau. For instance, 332 is this, and then the primary operator is an operator that cannot be derived from a total derivative of a previous d minus L minus 1 acting on phi to the n, right? So the number of primaries is the partition of L into n and minus L minus 1 into n. Okay, for L smaller than n, it has a very simple interpretation. So any partition of L minus 1, right, can be turned into a partition of L by just adding one box. If I add one box, this is already a partition of L into n, not L minus 1 into n. Therefore, if I want to find this difference, I just have to count all partitions of L into n and subtract those that contain just one box in the line of one box. But that corresponds to that I have to consider only partitions of L into n. This is the condition of partition L into n, with the condition that Li obviously is smaller than n, but also bigger than 1. And this bigger than 1, it's automatically, imagine that I even forget about my previous construction. Right here, I reconstruct that L cannot be equal to 1. This is what I was saying, that only omega minus of 1 is a descendant. It's not a primary. Here I see that already automatically. The same thing can be done actually for arbitrary L, because any Young tableau can be associated to the conjugated Young tableau is just transposition. And then you can convince yourself that the counting goes exactly the same way. Now, what about this Fock space structure? Now I can imagine that the counting almost works exactly the same way as what we had before, without even talking what those operators A are. I can now introduce those operators AL1, AL2, and so on. And the counting is precisely exactly the same. So what about primary operators? I can take phi, write it in terms of creation annihilation operators, right? I can invert it and write creation operator in terms of momenta and the fields, right? And then the action of this operator on the vacuum is obviously now given by this. This is what Misha was talking about in here, some polynomials. So now if I write expressions for the conformal group, I can now impose the condition that K minus, K0, and K plus annihilate a state. And that gives me a way of constructing primary states. If I consider a state with the highest spin, so it's not LM, but LL, then this is my initial ansatz. Now, if I act with K minus, you can convince yourself that K plus and K0 automatically annihilate this state. K minus generates something else. This one can be accounted for by modifying what I call the primary state like this, and iterating this procedure, it gives me this expression. So my expression is given by A0 to the power to certain power times A1 dagger. Okay. Now, if I introduce this operator ALL dagger with just like this, any primary state can be written in this specific form. This specific form allows me also, since it commutes with K, it is 0, any product of those operators is still a primary. The product of primaries in free theory, it's a primary. So basically what I'm saying, that any primary state can be written just like this, and remembering what was the expression, you can see that next term is actually suppressed. This one scales as n-1 factorial, and this is n-2 factorial. So this is the leading term. Then the leading term can be just rewritten as some new creation operator acting on a state with charge n. And in this way, we reconstruct just commutation relation between these two operators, the ones that we constructed from the cylinder. But that, at the same time, allows us to write those operators. I can obviously write the primary operator even here, right? But the leading term for large n is given just like this. So Zohar, this is going back to the question, what the primary operator is. So for large n, this is the prime. Those are the primary operators. Say it again. So the last comment, if you give me just 2 minutes, I'll try to wrap up. So the question is, those are operators with spin L. However, we do not expect that L can be arbitrarily large for this procedure to work. It cannot work for L comparable to n, obviously. But so how large n can be so that we can trust this construction? Actually, looking already in here, you can see, no, not here. Yes. I'm just saying in here that writing the expression for the primary state, the leading contribution is suppressed, the subleading contribution is suppressed with respect to the leading contribution as L divided by square root of n. So you expect that the breaking happens for L of order square root of n, if you want to write expression for the primary state. However, what is interesting is if you compute an observable, because that can be just an artifact of the choice of our coordinates. So if you compute an observable, say some correlator of, not a correlator, but like phi bar phi, right? If you compute the expectation value in this state, you see that it actually is given by expansion in L over n and not L over square root of n. And if it's L over n, therefore you can basically trust your computation up to arbitrarily large L if it's not higher than n, than charge. So spin can be as big as charge. However, for states, if you do not compute correlators, but you compute state, you want to specific expression what the state is, this one doesn't work, and that there is no way of making it into in L over n expansion. And but we can have, yeah, what I wrote before, this is the expression for, this is the exact expression in free theory, right? And you can basically say that for small n, it's dominated by the first term, but when n grows and when it becomes bigger than the square root of, when spin grows and becomes bigger than the square root of n, this is actually the behavior. So it's not dominated by the first term, it shifts. And that's why you cannot account it for in this perturbative computation. So I conclude here. I want to, so basically what what is done in this section is that there is a semi-classical computation that can be used to study large charge sectors of conformal field theories. The goal is obviously is to extend this approach to non-conformal theories. Okay, and like the next step can be first to investigate some Minkowski observables, for instance, and to understand how it can be, how this approach can be extended in this direction. So just as a last comment, we do not know what happens for spins that are even larger than the charge in this sense. No, of course, no. I'm saying in this way. I do not know what to. Sure. These vortices is great, but vortices are only for interacting theories, right? Here I'm saying it's a free theory. There are no vortices for free theories, right? So I do not know what happens for spin which is larger than square root of n or even than the charge. However, the counting that I presented, it still works in terms of this Fock space structure. So it suggests that there should be some profile, some classical profile around which you can still quantize and to get the results. Thank you. But just a bit louder, please. Say it again. Expand L over square root of n. Yes. No, but hold on. I'm saying that in the interacting theory, as Zohar said, we wrote a paper on this, right? In the interacting theory. Oh yeah. That's a no. I haven't done it yet. No, I haven't found the explicit solution for vortices. If this is what you're asking me, I don't know yet. Sure.
So, there are integrable, non-integrable models out there.
Mm-hmm.
Has anybody studied what happens there? That you take some parameter and like worse.
I don't know. CPN sigma models for large n. Large charge. Yeah, you sure. Okay. Mm-hmm. Okay.
Okay, so I think any further discussion will continue at lunch. So we should think the session again.
The idea was that I will say we work with showing pictures during the days of conference.
Okay, so that's now.
I hope everybody but today we have only 15 minutes. Maybe Arkady wants to say, okay, maybe somebody else, in the audience who has some contacts with memories.
Да. Я просто.
Something happened to Okay, that's
I
right.
can say something. very
Okay,
brief.
sure.
It's very brief. So when I first met Misha Voloshin, I was actually really intimidated by it. I was terrified. But actually talking to him was always a blast. So, you know, during seminars, he did not suffer fools gladly, as we say. So I was nervous. But actually talking to him, he tolerated. It was really a pleasure. And this is, I didn't know it was all this.
Okay, if there are no other volunteers, maybe we'll start lunch today a little bit earlier. Instead of 12:25.
So
Let's start at 12, right? And then we'll hear at 4:00.
yeah, at 2 o'clock, please come back. We'll have a really energetic talk by Maria. So, you're on your own for lunch. I did send some ideas for where we go. If you want further recommendations, just ask.
Remember how to not we
But I don't think this applies at the end. It's the same because he added
yeah.
but he's got added.
Yeah, that's what I was asking. Yeah.
Okay, I'll see you later.
Yeah.
You said that from side.
So practically it's kind of finished because I know I said but I think
Grab one.
did the same thing.
So, you were once denied that you said okay. What happened? Yeah, okay, remember? It was so why were you denied the visa? Or did you not work before? Yeah. My story is you have a lot of family. My sister. But that's not for a question. It's not different. Is this your jacket? Yes, but I'm actually giving you a group.
Well, do you know what is outside? There's also a cup.
Dangerous.